Okay, then. Nice. Okay. Hello, everyone. Thank you for coming along, and obviously, thank you for inviting us. So my name is Ben Steele. I'm the CTO of a company called Raphtory, who's based just around the corner, about just near Liverpool Street. And we build a temporal graph engine called Raphtory, which is both a Python library and a GraphQL server, depending on how you want to interact with things. And the general premise of this is to be able to kind of look at your data through time, but still keep this kind of like structure of the networks that hopefully we all love. I'm joined by my good friend Naomi Arnold, who's a postdoc at Northeastern University in the NetSci group, who's just opened up around the corner in St Catherine's Dock. And we're going to talk about both Raphtory and some of the work that we've both been working on over the last couple of years.
Great. Yeah, I'm presenting.
What's that, sorry?
You're not presenting.
Oh, it's not presenting? Oh, maybe it dropped it because of... Oh, I actually just dropped out the call. Okay. Oh, maybe I had to agree to the recording, and it was like timed me out or something. Okay, nice. Okay, perfect. I'm indeed presenting everyone. Cool. Okay. So just to give you a bit of a background on us and the kind of ecosystem. So I done my PhD at Queen Mary University of London, which is also around the corner. So just down the road in my lens. And as part of that, I started building Raphtory. So we were initially interested in dynamic graphs. So being able to have like a large scale system where you could stream different data sets in, maintain a large network, and then sort of run incremental analysis on it. As we were doing this, we kind of realized it'd be very interesting. I've got today's data. Well, should I be able to automatically compare that to yesterday's data, the day before, a year and a half ago, etc. And ended up turning this into like an event log for each of these vertices and nodes, vertices and edges, so we could, see how things change at any point in time that we were interested in. As I come to the end of my PhD, I didn't want to get a job, as most academics don't. So I ended up creating a company called Raphtory. With the goal of kind of creating an enterprise version of this with some of my co-founders who were seeing that the problems they were having in their jobs in blockchain analytics and in KYC and sort of in finance and banking, this tool was actually really useful. Naomi as well was a researcher at Queen Mary University of London, it's where we met, and has now swapped over to Northeastern, where she's been doing some very cool things that she'll talk about in a minute. And we also have a variety of contributors from different universities around England and around Europe. So Oxford, UPM in Spain, and UCL are some of the big contributors alongside Queen Mary and Northeastern. So the things, is this? Oh, this is very laggy. I'm just going to quickly change to the toggle Wi-Fi. You have the password bar? Yes. Oh, I think maybe I've already had it. Sorry, Edge room appears to be not good fit.
You want Wi-Fi?
I think I can just log in as a. Here. I think I'm in. You're sure. Sorry about that. Okay. Yeah, so in this session, we're going to go over initially what temporal graphs are, and why they are useful, and kind of why you're trying to do some analysis in this space, why you can't really use existing solutions for it. Go over Raphtory and some of the interesting use cases that Naomi and I have worked on. And then if anyone's interested afterwards, we can show some of the code, give you an idea of what this looks like to actually run things for yourself. If you have any questions during, please just let us know. I mean, obviously, if there's anything confusing, that would be great to know so we can, explain it further. Or if there's anything that's interesting, you think, oh, it'd be cool if I could do this. This is very much like an open session. I don't think this is like us shout at you for an hour sort of talk. So to start, what is a temporal graph? Or more specifically, for those of you that are new to the whole area, what is a graph? Just as I know Peter's fine with this. Anyone in the room not know what a graph is? Okay, cool. That's very, very good. So that's a good start. So the way that I tend to think about networks very, very quickly is that we go from tabular data, so rows and columns. We want to extract out the underlying entities and the relationships that they share. And this, to me, is a much more human way of interacting with data. You know, when I think about like how I connect to my friends, I don't think about it as a list in my head. I think about, oh, I'm friends with Laurie, he's friends with Chris. You know, this is very much the way that I like to think about things in my head. And on top of this model, we can apply a variety of different contexts. So yeah, again, we can think here of social interaction networks. So I'm a friend of someone, and if this is online, maybe I like someone's post. I can apply it to transaction networks. I send Naomi money, Naomi sends you money. Or we can think about this in terms of logistics. So this could be, you know, cities that have transportation links that may be via airports, they may be via roads, etc. There's a whole host of different use cases that we can apply given this model. What we end up doing in Pometry a lot of the time is taking real-world data, which doesn't necessarily feel like a graph, and turning this into a graphy problem so that we can do interesting stuff on it. So, for example, we had some data of ships traveling around the ocean, and we had this problem of this insurance company had lots of ships that were meeting in the ocean and trading goods. So you'd have like an American ship that would leave port, they would meet a Chinese ship in the Indian Ocean. The American ship would trade goods at sea. The Chinese ship would go off to Iran and break American sanctions by selling the goods there. But the American ship would dock in Dubai or somewhere along these lines and sell the goods on paper. So officially nothing has gone wrong, but actually there's this kind of like black market trading going on in the background. So we've been able to turn this into a set of nodes of locations and then see how the ships move around them so that you can sort of map this co-location as an example of some of the things that not necessarily look like a graph, but at least once you've massaged them a bit, turn into one. So all of these examples are what we'd, at least I refer to as static networks. So these are ones where I've got a big batch of data, I've loaded it into a graph, and then I do some analysis on it. And this tends to be, you know, this gives us good insight. But one thing that I think is really interesting is to kind of unlock the story within our data. We want to know how it's evolved. So to give an example of this, I like to think about this in the instance of a real story, in this case, the Lord of the Rings, where for those of you who've seen it or read the books, at the start, Gandalf's hanging around with hobbits in the Shire. And then he's off on his adventures with Aragorn and Legolas. So this is there's a change point, there's an arc that occurs in the story, and we want to be able to model this kind of shift in time. So you have these kind of two different time points. You know, most people tend to do this. If you've got snapshots of your data, you maybe have to go back sort of day by day, maybe week by week, depending on when you back things up. But what we want to be able to do is take any point in time and look at how the data looked like at exactly that point. So I say, you know, last Thursday at 3:02 in the afternoon, what did my data look like? I should be able to pull out that network and then compare it to others. So that's kind of the goal of Raphtory and what temporal networks are. I'll pass over to Naomi to explain a little bit of why we can't just do this with tools that are available out of the box.
Yeah, thank you. I just for a little bit of background on myself. How I got into graphs and temporal networks was through my PhD, where I was modeling the how networks evolve over time in different domains, and then towards the end of that became more about just sort of general metrics to analyze the temporal networks in a more sort of general way. But one of the things that I came across like very early on as a problem in doing this, especially with existing tools, is that you have power laws everywhere. And what I mean by that is networks, especially large networks, when you look at different quantities on the network, like the number of connections each node has, it tends to be very like a power law distribution, which then can often push algorithms into a worst case scenario, and other tools that might be used in big data scenarios like partitioning or MapReduce become difficult, because now even if you partition the graph, you've still got maybe one node that's got huge numbers of links. So this was a recurring problem with working with large networks.
How do you partition the graph? Because if it's fully connected, disconnected, how do you just ignore some of the edges?
So
Yeah.
I think there are heuristics for this, but you end up with a situation where the heuristics take so long to calculate that it's just not worth doing. So you can go, if you just go like a random partitioning, you basically end up with the same result. The other aspect of this as well is that because, let's say, and we'll come on to this in a second, if I say take 4 hops away, so follow 4 edges in the network, I basically touch the entire graph, which means that if I distribute this over, 10 nodes, and I'm following apart, I basically end up touching all partitions. So a lot of the time, and some of the work, so Raphtory started out distributed, and we've actually pulled that back onto a single node recently, because the amount of effort that it was to go distributed ended up in like actual performance reduction. Like, okay, well, actually, if we just vertically scale, we can store billions of edges, and it runs 10x faster than if we try to do this on like on a cluster.
And it all fits in memory.
It fits in memory with it, and there's some like extensions that go out of core and to spill to disk if necessary.
Yeah, and another problem that's more for the temporal networks is just having the expressibility to write what you want to get. So I did a little worked example here of using one of the more used network libraries, NetworkX, where if you wanted to say you have a big data set of social network interactions and you want to do a sliding window, getting the page rank or whatever your favorite metrics are, to sort of roll your own solution for that is involves you making mouse on there, having your time range, making filtering down the data, constructing the graph for each of those snapshots, and as well as like a few obscurers getting this to work, having the expressibility to do different things on top of that, say weekly, monthly, different ranges of windows. You end up rolling your own solution. And furthermore, it's actually quite an inefficient way of doing things in that if you have, say, a large data set or a large range of time points, you're constructing and throwing away graphs over and over again, which might have a lot of overlapping time points anyway. So it's not ideal for these scenarios. Then another thing with temporal networks is the algorithms for them can get out of hand quite quickly. An example of one which I'll touch on later is an algorithm which I was working on was looking for temporal motifs in this, where you have a sequence of edges that form a small subgraph. And for example, you might be looking for something like this, where it's incoming, then outgoing, then sending to another person. And if you want to look at all the different possible versions of that motif, this quickly blows up to 36 different times when you have this temporal ordering. And then I haven't even looked at if you have 4 edges instead of 3 and so on.
Can I ask a question?
Yeah, of course.
Well, what's a motif?
I'm probably going to that a bit later, but the motif thing that tends to refer to a small subgraph. And when you're looking at static graphs, so it might be something like a triangle, or you can have slightly bigger subgraphs like a small clique, and the temporal ones add an extra constraint on the time in which a motif should complete in the first stage, last stage, and
all possible combinations, all possible motifs are.
If you're restricted to 3 edges and up to 3 nodes, that's the all the different combinations with the sequences. So you've got some triangles, somewhere it's just on 2 nodes, and so yeah.
These represent graphs themselves. Is this a motif with 3 nodes and up to 3 edges?
Yes, so they're like patterns inside of the overall network. So the premise here would be is that I want to find how many instances of these appear in my network, and then use that as a way of categorizing them. So we'll come into this in a little bit in a second, but like this effectively, you could say you can look at this as a whole graph. So how many of each of these appear in my whole network, or from an individual node? How many times does my node appear in one of these patterns? And then you can then take that further, and you've got now a 36-dimensional vector, which you can use as an embedding elsewhere. So use this for prediction or understanding the kind of general structure of a network.
So it's like compressing graph, or is that what's the reason to do this?
So the reason to do this, again, we'll come on to some bigger example of it later, but is generally to understand, like even from an individual node perspective, like what does this node tend to do? So as an example, it might be like we have, imagine like if I'm looking at some traffic flow data, like some network flow data. If I'm a server that that's like a replica of some other server, I'm just going to have this pattern down in the corner. I'm going to send requests, I get an update to my data. I'm going to send requests, I get an update. If I all of a sudden swap into like a fanning out pattern where all I ever do is send to random nodes and get no response, these are two very different patterns. So the first one may be like acceptable. The second one maybe I've become infected with a virus that's trying to infect other nodes in the cluster. So there's different patterns may mean different things. And then you can utilize that to kind of classify or to cluster or to do a variety of other things down the line.
The motif itself is something that has a temporal component to it. It's like I don't know, the triangle forming and closing again, or is it something by itself static, just the appearance changes over time?
Yeah, you can have static motifs as well. So if you're looking for just in a static graph, for instances of like, I don't know, a wedge where it's just wedges are in triangles, but then the temporal motifs, and when you add an extra constraint on, say, the ordering of the edges or something.
So everyone finished taking computer then, like, does anyone want to have a second?
No, you go everybody.
Yeah.
So the static motifs are used with molecules, right? They use the molecules to classify molecules.
Yes, definitely.
But with the temporal one, I guess it just gives you more information.
Yeah, so I think that the temporal ones are useful when you have some sort of context in where this is important. So again, like one being the one I mentioned, another one which we're coming to is more of a financial example where something like the pairwise trading is indicative of like I'm just directly sending money between people. Whereas if there's a lot of planning out, then it's probably like I'm like in the crypto world, I'm an on-ramp. So like I may be an exchange, which is just sending money out to individuals. I don't ever really receive anything, but that's because I'm receiving dollars outside. So there's like you can classify individuals accordingly. Or it might be for a triangle. If I'm looking for a money laundering cycle, if this has got end hops, if I send money to Naomi, then she sends money to you, and then you send money back to me. This is much more of an actual cycle in time than like you send money to me, then Naomi sends money to you, then I send money to Naomi. This is like a
Because there are different time steps. You kind of find a cycle through the time.
Yeah, so you've got like order and duration of the additional like parameters that you're running on, which is why this becomes exponentially large because those are sort of open parameters that you can freely mess around with. Yeah, sure. But yeah, so those are kind of the general problem areas that we were initially looking at with Raphtory. So give you just a sort of brief overview of generally what it does. So the first thing that we were interested in being able to provide is being able to kind of attach and model data from anywhere. So a lot of the graph pooling that's out there that's not a direct Python library tends to make you sort of adhere to all their schema, so change all of your data to have specific headers, and kind of generally be the center of the universe in your kind of data ecosystem where everything abides by what they have. So we really wanted to avoid that. We wanted you to, if you've got data on disk, if you've got something in the cloud, if it's already in a pandas data frame, for example, you should be able to just kind of convert this into a network, do some graphy stuff with it, and then like push it downstream. So we have this pipeline to convert like data into a set of updates. So this node was added at this time, this edge was added at this time, this edge was deleted, these properties change, etc. That's then modeled inside of our temporal storage, in which you can actually load data in different, it's totally unordered. So if I have a load of data that's got jumbled timestamps, a load of other data that's got jumbled timestamps, as long as you adhere to this kind of update function call, everything will be sorted in terms of it. So we keep maintain a full chronological log. And then we expose a load of endpoints that allow you to query different things on Raphtory. So you can query it like via GraphQL, the Python library. It's actually built in Rust. So if you're using Rust, you can replace like petgraph, etc. And we're also working on a WASM library as well. So if you wanted to use this in JavaScript, you can actually embed it in the browser as well. So there's like lots of nice ways to interact with temporal graphs. One of the aspects that we're working on is to provide kind of all of the standard graph algorithms that you'd expect out of the box, as well as a load of interesting temporal ones, so such as the temporal triadic motifs that Naomi was talking about, things like temporal LPA, i.e. like community evolution, so just community detection, And also a nice API so that if you've written an algorithm or you find a paper which has an algorithm described, it's very, very easy to implement that in Raphtory and then utilize it alongside everything else. The final bit is that given that you know what algorithms you want to run, and hinting back to what we talked about at the start, you can also say like when I want to run my algorithm. And that can be things like an individual point in time. So like last Thursday at 3 in the afternoon, we can say ranges. So I know in one instance, which we'll come on to, someone had 400 years of data and they wanted to do like every year. I want to have a look at, how my graph changed. We can apply windows. So I can say, hey, look back the last day, the last week, or batches of windows. So, give me the graph every day, but looking back a day, a week, a month, and a year to see how things change in both the short and long term.
Does the graph need to already be stored in this temporal format? For example, is it quite difficult if you have two separate graphs, one from a year ago, one from today, and there's a big difference between them? They look the same, but it's quite hard to then detect what the difference is without having stored that delta.
So the way that this, we don't actually store any deltas, we store the full update log. So like if you pick out like me as a node, it'll say like my weight was 10 yesterday, it's 20 today, I was added 2 weeks ago, I was deleted tomorrow, something like this. And so when I then build on these views, this is just like a mask on top. So I'm never rebuilding or building deltas. I'm just looking at it for a particular lens. So in the instance of like, let's say I've loaded in one snapshot from a year ago, one snapshot from today, as long as if I ask a question on yesterday, it's going to say, okay, well, the last update for these nodes was a year ago. So I'm just going to view what that looks like. So yeah, I mean, the actual algorithms that you're running in terms of detecting the difference, there's definitely some subtlety to that. But what Raphtory allows you to do is basically explore any version and put it through the sort of pipeline where you detect differences. But yeah, I mean, you can also, as we'll get into, given an edge, or a node, I can say, hey, give me the history of this. And then I can do like anomaly detection or time series analysis, given that series of events. So you can view this as individual snapshots as in terms of discrete values, or as continuous values that you push into set of algorithms. So, I mean, really what Raphtory is kind of a tool that enables a lot of pre-processing and so on that you then push into, some time series library into PyG or some other like GNN-esque tooling so that's kind of the goal here, is to really enable the exploration before you do your actual machine learning.
And does the time between the updates matter? So say if you don't sample at the same rate, but rather sometimes cluster like frequent updates and then you have missing events or something.
No, absolutely not. So like everything is stored internally at the resolution that you set. So if this is days, if it's seconds, if it's microseconds, whatever it may be, and obviously you can mix and match those as well. So if you have a snapshot that's only days, and then you've got another set of data which is fine-grained milliseconds, you can push those both together, as long as when the time that you set is of a so if I mix like some random logical epoch like 1, 2, 3 with dates, I'm going to get some very weird things coming out. I mean, it'll still work, probably give you a strange answer, but as long as you're using dates to a degree in both of them, then this will work together nicely. Yeah, so they're kind of they're getting into the actual meat of the conversation. It's like, what can you actually use this for? It's good. I'm glad there's lots of questions at the start of this, but hopefully some of these will be answered now. So the first thing is like, you can take static algorithms that you may have already done, so connected components, page rank, triangle counting, clustering coefficient, etc., and just run them over different times and timescales. So as an example of that, one of the ones, this is the one I was talking about before, we had a company, a legal firm, that had 400 years of legal judgments, and what they were interested in is when judges cite each other as why they've given particular sentences or why they come to particular decisions, we can build this up as like a full citation network, similar to if you had like paper citations and so on. And what this company was interested in was, given all of the citations that happen around the world, how do different jurisdictions affect each other, and specifically how important is Britain in the kind of like global community of courts. So what we done was we ingested all of those into Raphtory, and then we were looking at a whole host of metrics and how these changed over time. So we were looking at, this is a subset, but from 1600 all the way up to 2020. And specifically, we were interested, in this instance, we're looking at the largest connected component over a set of windows. So this dotted line here, I'll use the mouse for those.
So what's the L? What does L stand for?
Oh, so that's the largest connected component. So it's like, this is basically how big is the main cluster of people that are communicating with each other. So it's like how fragmented is the network? If this number is really low, then it means that like very few, like, there's lots of small communities that are not talking to each other. If it's very, very large, it means that basically everyone's connected. So what you typically see is this is a very, very big cluster, and then you're a 0.8 and above. The vast majority of people are in communication, and then there's small like groups of people that are not communicating, but they don't really matter in the grand scheme of things.
Is this a measure of globalization then?
Effectively, yes.
Right.
So the interesting thing here is that you take the dotted line, which is the aggregate. So this is your sort of typical snapshot view. You get this kind of like, okay, the value continuously goes up, which is what you'd expect from sort of 1940 through to now. Technology's improved, and more people are able to communicate. The interesting thing is when you look at individual windows, so looking at things like the last 5 years for each year, or the last 1 year, you get these interesting dips and particular peaks. So we investigated what these were, and we found that, this one in particular, around 1960, was actually a lot of countries gaining national independence. So they've become emancipated from Britain and France, etc. And especially in like the Caribbean, they started to refer to their own legal system and that the United States instead of European laws. But then as you got the kind of rise of the internet and everything started to become digitized, even though we're now in a year, all of a sudden, all these people started like connecting back up. So this is maybe not the most interesting of insight, but what this kind of shows is that given the same algorithm running over different time spans, you actually get vastly different answers. So it's important when if you're doing some analysis on any of your data to kind of understand that, am I looking at an overall aggregate pattern, or am I looking at something that's happening in the short term, and which one of these is more important to me? The second one is that we can actually explore the history of entities. So this is what I was saying about like, this sort of time series analysis and so on. So for this is a blog post that we put up investigating shell and shelf companies. So we took a load of data from Companies House and had a look at basically who are the owners of these companies and how do these change over time. So we built this network of people, directors of companies, this is the sort of model. And then we were interested in like 4 individuals, how many companies do they own and how long do they stay owners of these companies? And we found some very interesting people just off the bat. So this gentleman here actually owns 50,000 companies, most of which last less than a week, which, I'm only a budding entrepreneur, but to me this seems very strange. He's doing a lot better job than I am, only have one. And when we looked into this further, he was running all of these companies out of this building here. Which I don't know how you fit 50,000 companies into a bricked up doorway, but I guess if need must. So when we looked into this further, he was actually running a phone scam for the Italian mafia and had just recently been put in prison. But he'd been doing this for 10 years. So it was wild to us that like something that we found within sort of half an hour of ingesting this data had taken this long for like the authorities to kind of dig into. We put this online, and this was around the time of the COVID support scheme fraud. So people were interested. A lot of people sent us the trust data, which was basically all the companies that have received preferential treatment by the government, and sort of sold this sort of bin bags to the NHS for millions of pounds. So we merged in this data with our original Companies House data, and then we looked at people that had significant control of companies, and we were interested in change points. So like if there was a shift in a company, what happened to them around that time that caused that shift? And again, we found some very interesting examples. So here's a company called Candy Boy Agency. They shipped millions of items from Cambodia that were like sort of like boxes of tissues and so on. They were sold to the NHS for £1,000 a box. And then the NHS actually re-auctioned them off at £5 a pop, which is over a 99% loss. And once £30 million had been extracted, this ownership shifted to an Isle of Man company with a very similar sounding name. And these directors said, no, I'm sorry, we can't give you the money back. We don't actually have control of the company anymore. So there's, a lot of the time, again, this sort of lights up very much. So it's like there's these drastic shifts following these kind of contracts being allocated. This one was actually exposed by the BBC. These people were thankfully arrested and the money was retrieved. But there's an awful lot of people that fit a similar pattern that I've not heard anything about. So we can only assume that they've kind of gotten away with it.
Can I ask a question?
Yeah, please.
Did you find any other examples?
Yeah, there's many.
That were not exposed.
That were not exposed. Yeah.
Did you recall them?
So we put a blog post out. We were in contact with Companies House because they'd sent us all of the data. So they have an open API. You can pull all this stuff yourself. But we sent them an email explaining what we were doing, and they sent us a full dump of all the records because it's all public data. So they were like, yeah, okay, please don't hammer the API. Here is everything instead of running it. But we have on a Python library. We have a Companies House provider which you give an initial address to, and then it like goes and finds everyone that's associated with it. So if you're interested in these sort of things, you can, there's a full notebook for Raphtory which pulls all the data and builds out the networks and allows you to do the analysis. But yeah, we reported them to the authorities in hope that they would something would happen to them. Who knows? I mean, the dream is that we get an email back saying, hey, people have been arrested, the money's been retrieved. It'd be quite maybe get back all 5 people doing means like yeah, exactly, yeah.
More generally, this is a knowledge graph. Right?
And this is effectively a knowledge graph, like
And the many other things we know.
yeah, for sure. I mean, like a lot of these examples here, these ones in particular, were more just us having fun with the tool and like dog fooding a little bit. So like, okay, we built a tool, can we do something that's actually interesting with it? And this seemed like quite a fun one. And obviously, like during this time in particular, there's a lot of people that are angry, or I imagine they still are angry about this sort of stuff. Yeah, and actually, so on that point, when we started speaking to a council, once we'd sort of had this data, and they were interested in using it to find illegal HMOs, so houses of multiple occupancy in their boroughs. This was a Lewisham council, and so they're estimating they were losing about £300,000 in revenue from like unpaid HMO fees and from people living in poverty and squalor, and 8 people to a house and all this sort of stuff. So the general problem that they had was that given a street which has a lot of houses in it, all of these houses are owned by different companies, which are either owned by an individual or owned by other companies, which are also owned by the same individual. So the biggest owner of property in Lewisham Borough is actually a random PO box in Luxembourg, for anyone that's interested in the wonderful world of London property management. And this, there's a huge array of this sort of stuff that's going on, and it's very, very difficult for the council with their limited resources to find actually who's doing things wrong. And the general premise of this piece was that given that one of these houses is found to be a legal HMO, there's a good chance that all of the other companies that are owned by this kind of web of corporations are also doing something dodgy, so they should investigate them. So we pulled data from Lewisham, data from HM Land Registry, and data from Companies House, merged all of these things together into a map or into a knowledge graph of buildings, companies. So Dodgy Landlords Limited here owns 14 up Brockley Road, and turns out I'm the dodgy landlord. But the premise here is that like we find this house is a legal HMO, and we can then like move this back throughout the network and find other properties that have higher risk. And obviously, if this other company down the bottom is also doing these things, the risk score can go up. So we can kind of propagate this risk throughout the network and then raise these kind of like high importance houses to check throughout. The other thing, so on what Plummetry does, we then visualize this for them. So we have this kind of network here where we can see all the legal HMOs and then other high risk associated properties. This allows people to kind of investigate the whole network, see how different companies are connected, and then decide where they want to send their enforcers to.
How do you measure the importance? Is page rank?
So yeah, so in this case, it's like if this individual in the middle owns 3 companies, which owns some huge amount of houses. So in terms of like where are the biggest offenders, we want to put those at the top, especially if they have a high number of illegal HMOs that have already been found in their network. So it's kind of a mixture of like centrality rankings, risk score association, and then a load of other features that can be brought in from other sort of analysis. So like how many people are paying council tax in that house, how many people are registered there on the electoral roll. So there's a variety of other measures that we can sort of mash together to come up with a final score.
I'm so curious to find out how you combine those. I had to go through a similar thing before. How do you combine like page rank and then the risk score? Do you just average them?
Also, yeah, this is the ultimate question. I mean, a lot of this stuff that we're still experimenting with. Like, there's we try to come up with some heuristic that decides what's more important. I mean, I guess in a lot of instances, it's also down to what the end client thinks is important. So, if the risk score to them is much more important than like, okay, I just want a list of who's definitely an HMO because I've got 2 enforcers for the whole borough, and I need to send them to houses, and every house they go to that's not a HMO is time wasted. So it's not so much about like, okay, this person has, they own 100 properties, so we're going to target them. It's like, okay, well, this one's definitely an HMO, let's go to those. So it's, yeah, I think it really depends on the use case for how you merge. I can't remember the exact decision we come to on this one, but that's, I think it's a very, very open problem. Yeah, and the final bit, kind of mixing both of these together, which I'll pass over to Naomi for, is this kind of mining of complex temporal patterns through time. This is moving into the crypto world.
Yeah, so this couple of examples here are almost combining the 2 aspects of looking through individual histories of individual entities, and then also applying algorithms through different times and time scales. And the example we were looking at was this dark web marketplace called Alphabay. I wonder if you've heard of Alphabay or Silk Road or anyways, if not, Alphabay was a like platform on the dark web where people could buy and sell things which often tend to be drugs. They also had some other illicit things like stolen data. Someone's done a big hack. They publish it to weapons as well. And the payments are made in Bitcoin, or were at the time anyway. And Alphabay itself was shut down in 2017 in this big, like, undercover operation by the FBI. But it's kind of an interesting ecosystem because while that one shut down, there were others that very quickly popped up afterwards. And so it's a bit of a like cat and mouse. Obviously, they're very resilient. And in this work, we had I did some transactions from Alphabay because they're publicly on the blockchain. And we were interested in sort of what we could find in terms of temporal patterns, characterizing different actors. So just a peek into like how it works and what we might be looking for. Alphabay and some of the other markets work via an escrow service. So Alphabay itself is considered as a user on the network. And let's say this blue user here wants to buy this parcel on the right that's being advertised. First, he makes the transaction for Alphabay, then hopefully receives the goods, and then gives the okay for Alphabay to release the initial payment. So it's like an escrow system for these. And so lots of the transactions are made up of these like marketplace through Alphabay itself. Other things we might see on there is exchanges where people have got an on-ramp for their Bitcoin, and so these entities which are sending out their Bitcoin to individuals. The other way around as well, people might be cashing out Bitcoin, so you might have people sending money to exchanges. But we have as well quite a lot of peer-to-peer transactions, so both like before Alphabay, but also maybe say these two have been buying for a little while and they trust each other. They might decide to start making transactions directly, cut out Alphabay in the middle. Or say another interesting thing, if you have heard of mixers, is that if you wanted to make the same transaction of the teal to the orange, but with a bit more privacy, you can do that via a mixer where many people wanting to make transactions essentially send all their Bitcoin into one node in the middle that's then dispersed to the intended recipients. So it's much harder then to recover the intended source and destinations. And how we studied that was using temporal motifs, and perhaps some of these different patterns might help motivate why we are looking at those. So a temporal motif is defined as sort of mentioned before, it's a small subgraph with directed edges in this case, and we impose the edges are time stamped. So in this case, we have 3 edges, time 1, time 2, time 3. And we add an additional parameter delta, which is the time by which the motif should have completed from the first edge to the last edge. And then if we're looking at instances for M, this would be an example of that motif, because those the difference between the first and last is less than delta. This one wouldn't be because the time span is too large, between 5 and 21. And again, this one wouldn't be because the edges are in the wrong timestamped order. So the motifs that we were looking for, we'll bring back this grid again, were motifs that happen on 3 edges and including up to 3 nodes. And I guess the main reason for that was that there's going to 3 edges gives us sort of enough range to explore all possible types of that motif. I think any larger would be that grid would be a lot bigger. So the interesting ones to point out there is the ones in this bottom corner might represent pairwise trading, where it's just 2 nodes involved. Motifs which are all outgoing, so it could be a user making a batch of purchases, or an exchange, or mix of splitting a transaction. And then the other way around, where it's all incoming in different orders, which could be indicative of like a vendor or a recipient of one of these mixed transactions. There's other things like triangles among that, or stars where the edges are in different directions. So we ran this on this data set transactions, just on the whole graph. And how we interpret this plot are the column is the first 2 edges of the motif, and the the row is the first 2 edges of the motif, and the column is the 3rd edge, such that we have the same grid as before. And by far the most prevalent motif in the graph is this fan out motif. So all outgoing transactions, and with the biggest type being like 9.2 trillion, which is quite huge compared to some others which were in just the hundreds of thousands. The single direction pairwise motif, so someone sending money to another individual, was also fairly common. And then the other all incoming motifs were quite common as well, but by much lower orders of magnitude. So we're interested in how this comes to be, breaking down both in terms of when these motifs happen in time, and also what happens when you break those down on the individual nodes. So what we look at here is breaking up those motifs over time. So what we did was looked at on a monthly basis the numbers of different types of 1-hour motifs, and how the composition of the most common motif changes. And we found quite a striking change in that in this first half of data, the most common are these green and blue, which represent 2 different types of motifs that are just on 2 nodes. Thanks, Peter. But then there's some point in 2016, it must have swapped over to this star type motif. And this is sort of around the time when some of the escrow services and this became more prevalent. But then this doesn't swap back to saying 2017, when Alphabay closes, we don't see it suddenly switch back to the original type motif, which suggests that maybe Alphabay has some like introductory role in introducing nodes to each other. And then when they break this down on nodes, by seeing which motifs the nodes participate in, find this very, very heavily skewed, where there's this one node who is responsible for almost all the motifs being all outgoing, and then another node that was in the top 10 for total number of motifs had all incoming as being the most. Yeah.
So if there is a node with all outgoing,
Yeah.
how do they get them on?
Okay. So they
is cashing out the money, right?
So I think it's more that like in this instance, they might receive one lump sum payment, which is like, I don't know, they get like 1 million Bitcoin in, and then all of their other transactions are fanning this out to loads of different places. So it's like all this, the other numbers aren't 0. It's just like
just the number of transactions, not the amount.
Yeah, so like
Yes,
proportionally,
yeah,
like
sorry.
this is like almost all, like 95% of it is like outgoing transactions.
I see. So there's one becoming, okay.
Yeah, they're kind of splitting this out into much smaller amounts.
But you will see the pound transaction, right? This will be only the Bitcoin side of things.
Yes.
Yeah, so that's something we wouldn't see any of that real world incoming. But then another interesting thing we found is that the market node, which we expected to have the most motifs as being the sort of central node, wasn't even in the top 10 for total number of motifs. Although it had this one here, which we would expect of it, which was represented by money coming in and then going out, as which is not consistent with it being an escrow service.
Can banks use this sort of analysis?
I would say so, yeah, very much so. Like you can, I think a lot of this, the interesting thing here is that what are the patterns that are typical for a particular user, and if those patterns change, then obviously this is, you at least want to contact them and say, hey, this is you doing these things.
Yeah.
So alongside the kind of analysis of like, is this where I'm sending the money to, is it in a new location? Is it with a person I've never spoken to before? Similarly, like what's the general trading pattern that I had for as an individual?
I don't know how often I've been on the same ice cream shop as they asked me
I was gonna say, yeah, because it feels like they have some very hard coded rules, right? Because their requests are so stupid.
So I spoke to some guys at Visa before, and they had the problem where because of their legal requirements, they can only use decision trees to make these decisions because they have to be explainable to lawyers. So like if someone's like, why did you block this? You can show them like a flow chart of like, here's why I blocked your transaction. So yeah, you can't like do anything that's even remotely black boxing. I mean, that might have changed. That was a couple of years ago, but I think that was the general problem.
One of the banks I worked with, they were trying to deal with the problem that they had different legal jurisdictions in different countries. And so they couldn't ship data, send us data across those boundaries, but they're looking for people like who have accounts in two different countries who are doing dodgy stuff. And this technique would be, you don't need to know the names.
Yeah.
They can't swap. They can't share, even though it's part of the same organization. So this would be very useful for that.
That's very, very interesting.
Yeah.
And if you know anyone that was worth chatting to about it, I'd love to.
I'll see if they're still involved.
Yeah, no, that'd be wicked. Thank you.
So I see we've got maybe skip the NFT example so we can have a bit more of a discussion at the end. Where this all work was, we hopefully might go eventually is to applying this further downstream to because having found motifs for each node in the network, we now have a feature that's in this 36 or 42 dimensions, which is the number of each motif that node is involved with. And we were interested with Alphabay, like, do you find some, let's say, in groups of nodes that have similar motif characteristics in maybe playing a similar role in the system? And after looking around some different embedding techniques, we were I think this was TSNE, and just doing a some k-means on the motif, the proportions of each motif. The sort of early results suggest that there might be some interesting clusters of nodes that have similar motifs. And in this particular case, unfortunately, we didn't have labels for each many of the nodes in terms of like this is a service or this is a vendor, but it would be interesting if there are other data sets where you can actually say a bit more about like maybe what each cluster represents or something. Yeah, I was wondering, shall I skip to
we can skip through this one.
Yeah, there's a blog post about this one, but it's
the general premise was that we were looking for money laundering cycles or wash trading in NFTs, and we found lots of it, which is probably not surprising to anyone. Yeah, we can skip half and go to the
about money laundering. Have you considered searching for money laundering schemes outside crypto? For example, if there is a data leakage, Panama Papers, whatever, can you create a knowledge graph, probably automatically, and then analyze that?
Oh, so
Anyone out there?
I think very much so. Like, the problem is a lot of the data that's outside of the crypto world is and nightmarish to get hold of. I mean, even some of the banks that we've been there is. I mean, we could definitely build things from say the panel page and then combine it with things like Bureau Van Dyke and with Company House and so on. I'd be very excited to work on it. But there's only unfortunately the amount of time we have for kind of like fun side things is like, so if someone wants to pay me for it, I'm 100% down. That would be absolutely amazing.
I think there's any apology had an example where they were building that's knowledge graphics.
Yeah, I think it was one of the like so they sold it to a load of journalists as like a way of investigating. Yeah, I think it's a very noble use. I mean, actually, so I was speaking to some of the neo guys, and unfortunately, the lady that they were working with got killed in an assassination. Her car was blown up.
Maybe you don't want to work on it.
Yeah, so that kind of like took the wind out my sails a little bit with these things. Yeah.
Economists does these things. There is a data section. They always analyze various data for various things. Maybe they want to look at it.
It's probably something that I should, yeah, it might be worth reaching out to. I didn't know the economist on that. I might see if they have a contact us and see if I can, hey, give me some data, or hey, do you want to use that tool? I was going to say actually on the point of these NFTs, because we basically found that there was like a very small cohort of people that were like doing market makers and trading around. And one of our friends done a PhD with us when he goes to the Tate Modern quite a lot. And he was talking to one of these managers at Tate Modern about like what's trading in NFTs and like how we could very easily find in like pump and dump schemes. And he said this man becomes visibly nervous. I like wanted to break away from the conversation very quickly. It's like that's it's interesting how people react to some of these things sometimes. We gave a similar talk at a crypto workshop, and there was a guy in the audience that was digging into it an awful lot. Like, he was very interested. So every now and then you find the people that you probably find. In terms of, we don't have automatic or anything, but sometimes people out themselves a little bit.
Previous company I worked for, they bookmaker, a lot of fantasy sports, but then they put in sports NFTs where you can, win a ball being thrown. And research suggests that a number of people love betting also love NFTs. And I'm surprised if there's a Venn diagram where money laundering is also right at the end.
Yes, I think so.
Money laundering casinos also just bet both sides. And
well, I realize I'm going to go back up, but very quickly on this. The cycles that we found were that so the duration of the cycles in days and the sort of length of people involved in the cycle was like a perfect L. So you have this first one here is that all of the cycles that involved like more than 50 people all happened finished within like a day. And the ones that went from $0 to $60,000 in terms of the NFT price all happened within like a day as well. So everything else that was kind of legitimate is just tinkering around at the bottom. And there's this big spike in someone buys a CryptoPunk or something like this, and all of a sudden resells it for $60,000, and then buys it back again for less money. It's a totally crazy ecosystem. But yeah, so then the final bit is if this is interesting to you, how you access it. So it's available on Cargo, on PIP, and soon will be available on NPM as well. When you download this, you can run the GraphQL server in Python, or you can run it as a standalone process. I think we're running out of time, but I can go into some of the code for those of you that are interested, or we can speak after this. But the general premise is that this small block of code here, which says kind of get me my graph, give a window of time, get me a particular node that I'm interested in. So this is some Reddit data. So we're looking at the conspiracy subreddit, and then do a rolling monthly window and look at some weighted average degrees, and then this will give you out this plot. So the actual kind of level of code is quite small for doing things that are sort of fairly complicated normally. You can find us on GitHub as well, obviously. We have a Slack if you're interested in going there. I'll go to the end so you can take your pick. If you use Raphtory in your research, I guarantee tier 1 papers. We're actually, as I said, just around the corner. So if you're interested in these things, we're more than happy to meet for coffee and chat. And as Barhead and I do quite often, whether it's about things that we've talked about or just generally the space, I'm always interested in talking about graphs. But yeah, thank you very much for having us and for listening. And if you have any other questions, please Love to hear them.
Thanks for the fun presentation.
Yeah, I hope it was on like at least okay in comparison to just going through a normal paper.
Yeah.
A mishmash of things.
Very nice.
Or I shall de-share.
Any more comments, questions?
Computationally, how long does it take to run? Can you be multi-threaded?
Oh yeah, so we rewrote the tool at the start of the year in Rust, and so everything is fully parallel. All of the operations that you can run can be vectorized. So I can say like, get me my edges, get these properties, do this aggregate on them, or like run an algorithm fully in parallel. So for example, the triangle count that Naomi was running, the motif tracking for ingesting on an Alphabay, so it's like 33 million edges. You can ingest this on a laptop in like a couple of seconds, and then I think the last run. How long was the last run?
I think it was about 2 minutes. So the night had been slightly shorter, but yeah, after a few optimizations, because they I was quite happy with the Rust rewrite, because in the last version of Raphtory, when first implemented the algorithm there, it took we were using like a big box to load the graph into memory and as your credits, and then it was taking about 2 hours or something, whereas it now works on a laptop in a couple of minutes, which is nice.
Yeah, so it's like it's a lot faster than it used to be, and yeah, it's so like the windowing and so on. So when you're building your views on top, these happen instantly because they're lazy operations. So if I say like I've got I want to look at every day over 10 years, that just returns you an iterator. So you can then pull out individual views of that. You can say get me this view and get me that view and directly compare them. And all of these are just kind of like maps on top of the underlying data. We've just released a new version yesterday, so 0.5, which has subgraphs, so you can do like remove nodes or like hide them away. We've now got multi-layer support, so you can have a look at like a variety of different relationships for like multiplex analysis, which is I think is really exciting. There's a load of pandas integration as well, so makes kind of the pipeline a lot nicer. Yeah, so there's a whole host of development going on. So yeah, so hopefully it's what I think it's well worth trying. But so yeah, it'd be interesting to see what sort of use cases you guys can apply to it.
Thank you. First public comment?
Yeah.